Hi, everyone. I have a question for you. Let's say that you're standing at a palm tree over here. You dig and you find a treasure map that will guide you towards your favorite band's concert tickets over here. Now, I have a question for you. If you wanted to know two bits of information about how to get from the palm tree where you are to the tickets over here, what two bits of information might be helpful? In fact, can you think of two different schemes? Can you imagine two different lists of two bits of information that can help you get from this point to this point? Well, one way is to follow the rectangular or Cartesian plane. Uh, Maybe the treasure map would say go 3 meters east and then let's say 4 meters north. And then you could dig and find your tickets. But what other pair of bits of information could be helpful aside from just horizontal displacement and vertical displacement? You might ask, for example, I'll put this in blue, how far are the tickets? What is the straight line segment distance between the two tickets? And then what other piece of information would be very helpful? Because if I just tell you how far the tickets are, then potentially your search path would be a whole circle, right? If I just tell you, oh, the tickets are 5 meters away, well, there's a whole circle that the tickets could be on. What else would help? A direction, perhaps in the form of a direction angle, theta. I'll call this r. R and theta, these are polar coordinates. So here's what we're going to do. We're going to talk about describing a vector. Let's say this blue vector over here. We're going to describe this vector in terms of Cartesian coordinates, like we did in red. That's more like thinking east and north. Cartesian coordinates versus, in blue, I'm considering polar coordinates. Whoops. Blue over here. I'm considering polar coordinates. Cartesian coordinates versus polar coordinates. Cartesian coordinates thinks more in terms of horizontal and vertical displacements. Polar coordinates are thinking in terms of distances and direction. Sound familiar? Magnitude and direction. Okay, so let's consider first the Cartesian picture. Vectors in the rectangular or Cartesian plane, based on a Cartesian coordinatization of the plane. We're talking about different ways of coordinatizing the plane. Coordinatizing the plane. All right, so let's let the vector v be given by this component form, where a is the horizontal component and b is the vertical component. Now, these symbols here are not parentheses. They're called angle brackets, and they're used to help denote components of a vector. Okay. So over here, the position vector for v, really it's a representation. The position vector representation for the vector v is drawn from the origin, that's the initial point, okay, to the point AB over here. That's using the classic parentheses. So we use classic parentheses to indicate a point in the plane. These angle brackets are used to indicate this vector, because remember, this vector can be placed here, where it starts at the origin, or it could be placed over here or over here. These are all equal vectors. They don't have to start at the origin. If we start the vector at the origin as the initial point, then we have a position vector or position vector representation. It's the most convenient representation usually for the vector v. Okay, so this is in terms of Cartesian coordinates or components. Now, what about the polar picture? In blue here, what about the polar picture? All right, so with the polar picture, theta here is a direction angle for V, and we usually take it to be an angle between 0 degrees and 360 degrees. We treat direction angles as standard angles here, where the initial side is the positive x-axis. Remember that the magnitude of V, or the length of V, is denoted like this. And actually in polar coordinates, we tend to use the letter R. So in this chapter, I'll actually use these two symbols interchangeably. In fact, R is what you get used to later on in calculus, like in Calc 2, Math 151 at Mesa. Although, as we'll see in Chapter 10, later on, we're going to consider cases where R could be negative, whereas lengths, like the length of V here, cannot be negative in Chapter 6. Later on in Chapter 10, we'll see that R could be negative, actually. That's if you go in the opposite direction. All right, so remember that if I take two distinct points in the coordinate plane, right? Maybe the axes are here, for example. All right, so if I take a directed line segment from this first point, x sub 1, y sub 1, to the second point, x sub 2, y sub 2, okay, then this is a representation for a vector, v. How do we get the components? Well, for the horizontal component, it's the change in x, and the order matters, okay? Unlike for slope, where there are two different ways of doing it, the order matters. It has to be the new x-coordinate minus the old x-coordinate. Remember, to get these components, it's got to be new minus old, right? The new x, the x-coordinate of the terminal point, minus the old x, the x-coordinate of the initial point. Likewise, delta y, okay, that's a change in y. It's got to be the new y minus the old y sub 2 minus y sub 1. It has to be like this, okay? And of course, for slope, we could do this over that, right? But with slope, we could actually switch these and switch these. Here, we're not allowed to do that. You cannot switch these, and you cannot switch these. It's got to be in the order new minus old, new minus old. I'll do an example of this later on. Okay, next up, we're going to convert between Cartesian, the Cartesian perspective and the polar perspective, okay? In a way, how do we go from Cartesian coordinates to this point? If we have a position vector representation here, how do we go from Cartesian coordinates for this point to polar coordinates? That's basically the idea. How do we go from A and B to theta and R, or vice versa? Next time.